This is the section 14.1 lesson video for physical science, and as always, if you subscribe to my channel, you'll have all my videos in the same place. So chapter 14 is on work, power, and machines. We're talking about simple machines. But today we're just going to focus on section 14.1, which is just on work and power. So in science, work is the product of force times distance. Remember, product mathematically always means multiplying, so work equals force times distance. Work is done when a force acts on an object in the direction the object moves. That's the important part, because a lot of times in examples you feel like the person's doing work, but because their force is not in the direction the object's moving, the work is not being done. So for a force to do work on an object, some of the force must act in the same direction as the object moves. And then if there's no movement, then no work is done, because work is force times distance. If there's no distance, then anything times zero is just zero. So for example, this person pushing up against the wall. I may feel like I'm doing work. I may push so hard and not feel like I'm doing work. So I'm applying a force, but is the wall actually moving? No. So since there's no movement on the part of the wall, there's no distance. So there's no work being done. Alright, so your important thing to remember is the force has to be in the same direction, or at least some of it has to be in the same direction as the movement of the object. So diagonal forces, that's why we say it has to, some of the force has to be used, because if you're pulling in a diagonal motion, but the object is just, say I'm pulling kind of like this, but the object's going like this, some of the force is in the same direction. So a force does not have to act entirely in the direction of movement to do work. Any part of the force that does not act in the direction of motion does no work on the object. So if you are pulling in a diagonal motion, but yet the object is just going this direction, the upward part of that diagonal force is not doing any work. It would only be the horizontal part. So let's see if we know what work is. So remember what I told you. The force has to be in the same direction as the object's movement. A scientist delivers a speech to an audience of his peers. You may feel like he did a lot of work, but did he apply a force over a distance? No, he did not. A bodybuilder lifts 350 pounds above his head. Well, if he's trying to lift, he's going in an upward motion. Would the barbell also be going in an upward motion? Yes. So his force is upward. The barbell is going to move upward. So that would be a yes. Lifting things is always work. So if I pick something up, that counts as work. This is where it gets tricky. This is number 3. A mother carries her baby from room to room. Now notice I didn't say anything about lifting up the baby. So she's already holding the baby and she's just carrying the baby. Well, what's the direction of her force to hold the baby? Well, to keep the baby in her arms, her force is upward. But she's moving horizontally to go from room to room. See how my movement is this way? But my force to keep the baby up is in an upward direction. My motion's in this direction. They're not the same direction, so this is no work done. And this is where it gets tricky, because like if you're holding a baby for a long period of time, even though it wasn't that heavy to begin with, you realize after a while it is starting to get so heavy. But you're technically, scientifically not doing any work at that point. Now when she picks the baby up, that's work, because she's pulling the baby up, the baby's coming up. But once you just hold something and carry it around, now you're walking horizontally, but you're holding it up, so those are not in the same direction. Alright, a father pushes a baby in a carriage. Well, if you're pushing in a carriage, I'm pushing this direction. Is the carriage also moving in this direction? Yes, it is. Okay, so pushing something in the direction that it's moving is considered work. Alright, now because a lot of people miss number 3, I threw in number 5. A woman carries a 20-kilogram grocery bag to her car. So again, notice I did not, I don't know why there's a question mark there. My typos. So again, we don't say anything about picking the grocery bag up. We're just saying she's already picked it up and now she's carrying it. So remember, her force is in the upward direction to keep the grocery bag in her arm, but she's walking in a horizontal direction. So remember, carrying things, picking them up is work, but just carrying them is not work. And that is a common misconception. Alright, so let's look at how do we calculate this stuff. So work equals force times distance. So we've already talked about force before, back in chapter 11. So force is in newtons. Remember, a newton is a kilogram times meters per second squared. So force is in newtons. Distance is going to be in meters. So when you do a newton times a meter, nothing's going to cancel. You get a newton meter, or a newton times meter. So when you get a newton meter, we turn that into a joule, which is represented by a capital J. Okay, so when you solve for work, you're more than welcome to write your unit as N times M, newton meter, or it's easier just to remember to change it to joules, which would be a capital J. So it says, if a man pushes a concrete block 10 meters, so there's my distance, with a force of 20 newtons, so there's my force, how much work has he done? So we're looking for work. So work equals force times distance, so then I just plug in. So my force is 20 newtons, my distance is 10 meters. So once I multiply, I'm going to get 200, and then remember, a newton meter is a joule. So he did 200 joules of work when he pushed that concrete block. All right? So next, let's talk about power, and then we'll go back into the math a little bit more. So power is the rate at which you do work. Whenever something says rate, that means how long does it take you. So the rate at which work is done. So doing work at a faster rate requires more power. So two people could do the same amount of work, but if one of them does it faster, they were more powerful, even though they completed the same amount of work. To increase power, you can do one of two things. You can increase the amount of work done in a given amount of time. So if somebody does more work than another person, the person who did more work is more powerful as long as they spent the same amount of time. Or you can do the same amount of work in less time. So for example, this man, he's running. Let's say he runs a mile. He sprints it. This lady, she's just walking a mile. Well, they're both going to travel 1 mile. So they'll do the same amount of work, but obviously he's going to do it a little bit faster. So he is going to be more powerful. And by a little bit, obviously a lot. Look at him. He's clearly a professional. This lady just looks like she's just walking on her day off. All right, so power deals with how fast you do work. So the formula for power is work divided by time, or work over time. So we've already talked about work. Work is going to be in joules. Time is going to be in seconds. So a joule and a second are not going to cancel, so you're more than welcome to put joules per second as your answer. Or a joule per second is a watt. So think about a light bulb. Power runs through and lights up a light bulb, and a light bulb is in watts. That might help you remember watts. And watts is just a capital W, and that's the SI unit of power. So like I said, you can do either. You can do joule per second, or you can say watts. But you got to have a unit. You know I'm picky about units. So it says 2 physics students, Ben and Bonnie, are in the weightlifting room. Bonnie lifts the 50-kilogram barbell over her head, approximately 0.6 meters, 10 times in 1 minute. So she lifts it 10 times in 1 minute. Ben lifts the same 50-kilogram barbell, the same distance over his head, 10 times in 10 seconds. So she does it 10 times in 10 minutes. He does it 10 times in 10 seconds. Which student does more work? Well, that's tricky because they both do the same amount of work. They both lifted the same 50 kilograms over their head 10 times. It was the same amount of work because they said it's the same distance over their head. All right, but then it says which student delivers the most power. Well, who did it faster? Ben did it faster, so Ben is the more powerful. Okay, so they both did the same amount of work, but since Ben did it faster, he's more powerful. So let's look at a little bit more math. So how much work does a 25 Newton force, so there's my force, do to lift a potted plant from the floor to a shelf 1.5 meters high? So there's my distance. And of course, we're looking for work. All right, so as always, maybe pause the video for a minute, try it on your own, and then check back and see if you get the answer right. All right, so let's do it together. So work is force times distance. So then I just plug in. So my force is 25 newtons My distance is 1.5 meters. So when I do 25 times 1.5, I get 37.5. And so then remember, I'm going to get a Newton meter, which we said for work is a joule. Alright, so hopefully you got that one right. If you didn't try that one on your own, try this one on your own. But just pause it, try it on your own. So it says how much force, so this time I'm looking for force, so we're going to have to rearrange that formula. How much force is needed to complete 72.3 joules of work, so there's my work, over a distance of 22.8 meters, so there's my distance. Okay, so we're going to have to rearrange that formula. So work equals force times distance. I want to solve for force, so I want force to be by itself. Remember, the way you move something to the other side is by doing the opposite mathematically. So I need to get rid of distance. Well, right now, it's multiplied by distance. So what's the opposite of multiplication? Division. But if you do it to one side, you got to do it to the other side. So force is going to be work divided by distance. Because see, the distances cancel on this side, but when I divide it on this side, it does not. So once I've rearranged my formula, I can just plug in. So my work is 72.3 joules, and my distance is 22.8 meters. And so when I divide, I get 3.17. And then what is our unit for force? Well, it is newtons. Now let's say you forget because you see this joule per meter. Well, if you remember, a joule is a newton times a meter, and we're dividing it by another meter. So those meters cancel and we're left with newtons, which is what we have right here. All right, so hopefully you're getting good at rearranging those formulas. That's something you got to be able to do. All right, so I'm going to erase. And of course there's my answers. So let's look at some more. So again, try these before you watch me do them. So it says, you exert a vertical force of 72 newtons. So there's my force. My gosh, I made that one really high. I can barely reach that. To lift a box to a height of 2 meters. So there's my distance. In a time of 17 seconds. So there's my time. How much power is used to lift the box? Alright, so I'm looking for power. So our formula for power is work over time. Well, do I have time? Yes. Do I have work? No. I have a force and a distance. So sometimes you have to do double formulas. Because do we know the formula for work? Well, yes. Work equals force times distance. So if I can figure out my work, I can then plug into my power formula. Okay, so you got to be aware that sometimes you may have to do a multiple step problem. All right, so let's do work first. So work is force times distance. So my force is 72 newtons, and my distance is 2 meters. So I would do 72 times 2, and that ends up being 144. And then a newton meter is a joule. So see, now I have work. So now I can use my formula to do work over time to get power. So power is work over time. So my work is 144 joules. My time is 17 seconds. So when I do 144 divided by 17, I get 8.47. Now remember, my unit is joules per second, but we know that that turns into watts, which is a capital W. And so don't get confused. Like, that's the only thing I don't like about watts, is because a lot of people want to put watts with work because they're both W's. But remember, work is joules, power is watts. All right, so again, try this one before you look at my answer. So it says, if you lift a book from the floor to a bookshelf 5.4 meters above, so there's my distance, from the ground, how much power is used? So I'm looking for power. If the upward force is 15 newtons, so I have a force, and you do the work in 2 seconds, so I have a time. So this one is very similar to this one. I'm looking for power, and we know power is work over time, but I haven't been given work anywhere. I've been given force and distance, so I need to use my work formula to get work. So work is force times distance. So my force is 15 newtons. My distance is 5.4 meters. So when I multiply those two, well, I'm going to have to click so my answer comes up there. When I multiply those two, I end up getting 81 joules. Because of course a newton meter is a joule. And so now I can plug this number in for work. So power is work over time. So I plug in my 81 joules over my 2 seconds. And so once I divide, I get 40.5. And then a joule per second is a watt. Remember, power is in watts. Work is in joules, power is in watts. Okay, so hopefully you got at least one of those right, if not both. So like I said, once you learn formulas, be aware sometimes you have to use one formula to get something to plug into another formula. And so of course there's my answer down there. So let's hit this section assessment real quick. So it says, what conditions must exist in order for a force to do work on an object? Well, remember, for a force to do work on an object, it must be in the same direction that the object is moving. Okay, so the force must be in the same direction as the object is moving. So what formula relates work and power? Well, the only formula we know that has both of them is power equals work divided by time, or P equals W divided by T. So power equals work over time. Number 3, how much work is done when a vertical force acts on an object moving horizontally? Okay, so this is the carrying example. A vertical force acts on something moving horizontally. How much work is done? None. No work is done because they're not in the same direction. All right, number 4, a desk exerts an upward force on a computer resting on it. That's why the computer doesn't fall into the desk. It's back to Newton's laws of action and reaction forces. The computer's pushing down on the desk, so the desk must push up on the computer. That's why it doesn't fall through. So a desk exerts an upward force on the computer resting on it. Does this force do any work? Well, remember, work is force times distance. Is the computer that's sitting on the desk moving? No. It's just being held in place. So since there's no distance, there's still no work done. Okay, so 2 times there's no work done. If there's no distance or no movement, there's no work done. Or if the force isn't in the direction of the object, no work is done. Okay, so both of these examples, no work is done. All right, so again, pause it real quick and try it and check back with me. So you lift a large bag of flour from the floor to a 1 meter high counter. So there's our distance. Doing 100 joules of work, so there's our work, in 2 seconds. So there's our time. How much power do you use to lift the bag of flour? So we're looking for our power. Okay, well, power is work divided by time. So, is there extra information on this one? Yes, there is. Do we even need distance at all? No, we don't. And that's another thing that throws some of you off, is if I give you extra information, you feel like you should use every number in the question. Well, we only need work and time. I don't need to know that the height of the counter is 1 meter. All right, so I just plug in. So my work is 100 joules. My time is 2 seconds. So obviously, 100 divided by 2 is 50. And then you'll get joules per second, which, as I told you, the SI unit for power is watts. So 50 watts of power. So hopefully now you have a good understanding of how to calculate work and power and when work is and is not done.